All right. So we had a homework due last night. I was not in a rush to release the next homework because I think it's gonna be, I have 2 weeks for it. There are only 2 assignments left really in the class. There's a large last one that I might break down into 2, depending on where we are and how far we get. But my plan is only to have a couple more homeworks. So I think they can both last a couple weeks. Are we planning an exam next week? I forget if we planned an exam for next week or the week after.
That feels a little bit too close to the last one.
Yeah, it should be weeks. What did I have? 3, 6, 9 in finals. So we're definitely not to. We're not to week 9 yet. So it's probably 2 weeks away.
Yeah,
All right.
so
So we're not worried about that yet. Not worried about a study guide for tomorrow. That'll be a week from tomorrow. All right, last time we were talking about Turing machines and this concept of the most powerful possible automata. And this is how we were going to visualize it. We have a control unit like we've had prior control units for automata that hold the states and transitions. But now we actually are producing output and reading not just from a single input string, but the entirety of this infinite one-dimensional tape. So it's infinite in both directions. So we can move left an infinite number of times, or we could move right an infinite number of times. The only thing that we are constrained by is time. So infinite memory again. Let's take a look at the formal definition, because we've done this for every one of them. We, in addition to our set of states and the input alphabet, we're going to have another symbol here for the tape alphabet. So it is separate from the stack alphabet, but you can just think of it as any possible symbol that could appear on the tape. Just like we could add different symbols to the stack, or we could read different symbols in the alphabet. The idea is that we can write some additional things on the tape that are not just in the input alphabet. We just need to define what those symbols mean when we are supposed to read them and write them. What is the logic associated with when I read this symbol in this state? What should I do? There's a special symbol now that is part of the tape alphabet that we're going to call the blank symbol. It's just an open-faced square. This is the equivalent of the null character in programming. It just basically means nothing or empty, or it's not an empty string. It's straight up null. Inside of the control state, all we care about is an initial state, a set of final states, and then the transition function as we've seen before. So how are we going to write a transition in a Turing machine? Here we have it down on the bottom. We will have some change. And so we need to know what the current state we are in is, as well as the symbol that we're going to read in the tape alphabet. That tuple gives us our state. So the internal state of the control structure and given wherever this read-write head is on the tape, this is what tells us the current cell we are looking at. Whatever symbol is in this, the combination of state that we're in, symbol that we're reading determines the overall state of this Turing machine. So that's the input. To derive the next state that we're going to be in, we need to transition from some state in here to a new state. And that new state will be defined by the transition function. Any of the out edges that are possible in this state will arrive in a new state. We will write a new symbol to the input wherever we end up. And then we will move either left or right. So that is how we're going to read or think of a Turing machine transition. state we're in, the character on the input tape is the input. This will lead to a transition where we arrive in a new state, could be the same state. We're gonna write a symbol onto the tape, could be the same symbol we read, could be something that's different, and we're going to move left or right. So an example move here. Here we have a tape of 3 cells that we care about. The internal state of the control is Q0. And we see that there's an A on the tape. So this tuple tells us how we're going to transition. The resulting transition says, go to internal state Q1. So there's a transition in that control that's kind of out of the view of the tape. We're going to transition from Q0 to Q1. We're going to replace the A with a D. And then the pointer here is going to move 1 cell to the right. The read-write head moves. And now the next input would be, we're in state Q1, there's a B on the tape where we're currently looking. So how could we transition from there? We'd have to look back at the transition function to figure out what the possible moves are. Questions on the notation for a Turing machine transition? All right, so let's try to figure out what exactly a Turing machine is. Get a little bit better intuitive sense of this structure. We can think of it as a simple computer, right? It takes input and it produces output. This has not been possible in any other automata that we've looked at. Mainly, it doesn't produce output. It reads input and it makes a decision, yes or no. It's an acceptor. However, a Turing machine can now produce output based on whatever is on the tape when the program finishes. So now it can actually convert input to output, which is exactly what our computers do. Every program that we write takes input, produces output. Every method within a program that we write, a sub-program, takes input and produces output. So that's as basic as we can, a way to define computation. The logic between the function of the input to the output. We have a processing unit. The CPU has finite memory. That's the control unit. Knowing which state we are in and the associated transition functions, that is some kind of processing unit. It has finite memory because we can only have a finite number of states. We have the tape as storage. So you can think of it like a hard disk. You can think of it like a very basic SSD. Does not have that level of capability. Well, it does, it's just going to be slower. However, the instructions that we can work with here are quite limited. All we can do is sense input. Based on that input, we can decide what to do. And we can rewrite a symbol on the tape, change the state of the control unit, and move left or right. That's it. So the question that I have now is the Turing machine, as we've defined so far, deterministic or non-deterministic? It is certainly deterministic, yes. Why?
They can only do one thing based on what it sees.
Sure. We only have the ability to know or do one thing. We could make it non-deterministic if we allowed some aspect of the control to say, now you can go to multiple different states at the same time, but the machine wouldn't be able to simulate those multiple states because the machine exists in a physical form or a digital form, if you want to think of it that way, but we would have to be able to split the machine into two different realities and have them each perusing a different possible problem in that branch. So it is not inherently non-deterministic. If we're thinking of writing a program to run on a Turing machine that will actually do these calculations, then the associated algorithm needs to be deterministic. We can't have this machine forking itself. So make sure that if you're writing this to be an actual computation, that the transition function must define at most one move for each configuration. This means that we cannot introduce non-determinism into our control unit. Given any possible input state, and we talked about that input state being, I think it's easiest to see right here, this tuple, as this tuple is defined. So a state and input symbol, given that there should be only one possible transition. So that's what it means to be deterministic. All right, so what do we think the limitations of a Turing machine are? To phrase that in a slightly different way, what can a modern computer do that a Turing machine cannot do? And don't think in terms of complexity, think in terms of what kinds of problems can a modern computer solve that a Turing machine cannot solve?
Are there any?
That's a great question.
I guess that's what you just asked us.
Yeah. What if such a program existed? What would the characteristics of that program be?
Like, I'm pretty sure I've heard something of like, if some programming or programming process is Turing complete, then it can do anything, and that's like the standard.
Turing complete means that it can simulate any other Turing complete system. So if we define something to be Turing complete, then we could simulate any Turing complete system with that system. So example Turing complete systems are the game of life. If anyone has programmed that in your history, another example is Magic the Gathering. So what's really interesting is you could take the rules of Magic the Gathering and with that design the game of life, such that the game of life would be simulated within the rules of Magic the Gathering. Likewise, you could do exactly the opposite. You could take the game of life and you could construct the rules for Magic the Gathering using only the on and off cells and rules of that with the game of life. Has this been done? No. What has been done, though, is simulating the game of life with the game of life. Okay, I have to show this now. It's way too cool. Everyone needs to have seen this at some point. Let's see if I can get some audio in here. I don't know. The audio isn't actually important. It's just eerie music. So who in here has heard of the game of life or knows the rules of the associated game of life? So everybody? Excellent. So it will not surprise you then, music. It will not surprise you then that this is the game of life. This will slowly zoom out. You're right. Just in case you didn't know this was epic, the subtitles tell you that. Yeah, we have the game of life within the game of life, which means we could have the game of life within the game of life within the game of life, which means that, yeah, basically that's an example of a Turing complete system simulating a Turing complete system. But the academic paper that proved that Magic the Gathering was a Turing complete system was a very interesting read. It actually is it's quite a process. You can imagine the level of emulation that is needed to run a system within itself. How much more complicated is it to define the rules of some other game or other system within that system? This is why emulation is so challenging. When each new video game system has a new emulator for it, the actual underlying computation to be able to emulate it is that much more complicated than the system itself. Because you are not just reproducing, you are simulating. Which is interesting. When you convert one system like that to another, all of those transition rules need to be defined. How does one move from one large game of life state to the next large game of life state? Zooming in, that's a ton of rules in the underlying system. But anyway, distraction aside, I just find that to be really cool. So the answer to this question is there is nothing. A Turing machine can compute anything that a modern computer can compute. It's just the basic rules for why that can happen. So a Turing machine program is significantly more complicated than a modern programming language program. But let's talk about how to design some simple programs so that maybe we can start to understand some of the underlying logic of the programming languages that we've been using in all of our classes. This is where we start moving toward the theoretical aspects of computer science in the class, making a lot of good thought experiments for the future, but also starting to understand just how does this programming that we do on a daily basis break down into just raw logic. So how does the program work? We start in a starting state, an initial state, just like we have before. So of the states in the Turing machine, we need to define what is that initial state. We'll have some initial information written on the tape. This is the program's input. Starting wherever the read-write head is on the tape, and using starting at the initial state in the control unit, we'll just go through the transitions defined by the transition function. And as this happens, we will be transitioning the input into the output. We'll be taking the input and defining where the output is and what the output is. Eventually, the process may terminate, which means that we have a halt state in the Turing machine that basically says program over. So we can define transitions to that halt state, depending on when we reach what would be considered to be a final state, we will move to halt. And if we went to halt from an accepting state, then we accept. If we went to halt from a rejecting state, then we reject. And that is the way that we will build an acceptor in a Turing machine. So when we reach a final state, or when no transition is defined, we can move to a halting state. On the other hand, So I guess we can start here. The transition function, like an NFA, is only a partial function, which means if no transition is defined in the current state, then we automatically halt and reject. It may not terminate. It is possible to get stuck in an infinite loop in a Turing machine. And technically, it's been possible for us to produce an infinite loop in NPDAs as well, as long as you have a lambda transition, meaning there's no characters read, and a lambda transition back. So put an A on the stack, pop an A off the stack, put an A on the stack, pop an A off the stack, and don't read anything in the input. We'd get stuck in an infinite loop. So we've had the ability to do that before, but it's going to be much easier to do with a Turing machine, especially on accident. So let's take a look at one such example Turing machine. Here are all of the rules associated with it. Take a look at that for a second and see if you can identify what this looks like. What is this Turing machine doing? You can use an example to try to figure this out. Any guesses? What's this Turing machine doing?
It replaces the first thing with a B always, it's like, unless it's null, then it goes to the accepting state and keeps it null.
So what happens if we started with the read write head over the first A?
It'll write the first A and then B and move the head to the right.
And then,
at that point, we see another A, so it'll do the same thing.
yes. So it ends up looking something like this. We're in state Q0 with the read write head at the first A. So we look for a transition that's defined Q0 on A, which is this first transition. So it's going to stay in state Q0, write a B, and move right. So we take this A, we write a B, and we move to the right. We're in state Q0 and C and A, so it's this same transition. We're going to replace that A with a B, and we're going to move right. Now we see the blank. There's nothing on the tape here. So when we're in state Q0 and we see the blank, then we're going to move to state Q1, write a blank, which is exactly what was already there, and move left. Since Q1 is defined to be the final state, we halt. So what this did is it transformed all A's in an input string to B's. Note that it would not have changed any B's. If it read a B, it would write a B. So this just turns all A's and or B's into B's. Questions on any of this logic? We can use transition graphs just as we have for all of our other automata. So this looks like this. In Q0, we loop to Q0. When we see an A, so read an A, write a B, move right. Read a B, write a B, move right, is what those three things say. And then the transition from Q0 to Q1, read a blank, write a blank, move left. And since Q1 is final, we move to a halting state. Questions on this view of a Turing machine? I'm sure I will say this momentarily, but we're going to start moving away from visualizing Turing machines as transition graphs, because even more so than NPDAs, they look gross as your program blows up. And unlike with NPDAs, for most languages that we care to represent with a Turing machine, or most programs that we would want to write with a Turing machine, we do not want to visualize the inherent transition graph. It's much easier to write them like assembly instructions with headers. All of these transitions do this logical aspect of this program, and then break them down into groups, because most Turing machine programs will have, even simple ones, have 20 or 30 transitions defined. And seeing that in graph form is really hard to parse. All right, following transition graph of a Turing machine, assuming the tape has an A and B in that order with the read-write head pointed at the A, what does the machine do? Ready? There it is. Yes, it is. Why is this an infinite loop?
It reads a character and then goes right, and it reads the character goes left, and we're back to the same character that took it right.
Yes. So no matter what we see in the first cell, we're going to transition to the right and not change it. Whatever symbol we see when we get there, we're not going to change it and move back left. So it doesn't matter which symbol is there, we're just going to be moving back and forth. So it's worth at least having some kind of intuition about what the simplest possible infinite loop might look like if you see a more complicated version of this in something that you produce. Just like before, we can use instantaneous descriptions to describe how a Turing machine makes a series of transitions. So we need to know the current state of the control unit, the contents of the tape, and the position of the read-write head. So it's way more involved than an instantaneous description of an NPDA, especially if the tape has contents. So we draw something like this, where we're going to be writing down the entirety of the contents of the input string. We're going to put the internal state in the middle of that tape, of those contents. So if there are some number of things here, we said we're going to write A1, A2, all the way up to A sub k minus 1. Then before we get to A sub k, we're going to write that we are in state Q, and then write everything from A sub k on. So this string tells us everything that comes before the state, the current state, and everything that comes after the current state on the tape. Where this is pointed is where this Q shows up. Does that make sense? There's a bit there.
So is the Q just where the header is pointed?
Yeah. Okay. So we'll name it whatever the name of the internal state is, but we'll put it at the position of the read-write head. Anything that's unspecified is assumed to be blanks. So transitions in this form, we can now use that same turnstile symbol from NPDAs, and we can define the move from one configuration to another. So let's get an example of this. Here we have a rule. In state Q1, we read a C, we move to state Q2, write an E, and move right. The tape just has A, B, C, D written on it. So go ahead and assume that the read write head is on the C. Go ahead and give the entire instantaneous description form of this transition.
Is it before or after the transition happens?
You're gonna, so you have the instantaneous description of the before, the turnstile symbol, the instantaneous description of the after. We have an answer? Yeah,
I got AB Q1 CD turnstile AB Q2 D.
I think that is right. I think that is what you said. ABQ1CD turnstile ABEQ2D. So how we got there, we had the string ABCD. And we knew the read write head is pointed at the C. And we said that the state that we're in comes before the place where we are pointed at. So that says the current state we're in, Q1, should go right there. Now we actually follow the associated transition. We know that this transition reads the C, writes an E, and moves right. So the C is going to become an E. So we have A, B, since we moved right, the Q1 should be one position. So this state, Q whatever, should be one state to the right. So we're gonna have the E that we wrote followed by the state, followed by the last D. So this moved one space to the right, and this wrote. It's a right instruction to replace the C with the E. Those are the two things that happened in that transition. And I guess the change from Q1 to Q2. Questions? Put the eraser probably over there. Grumble, grumble, grumble. All right. We saw that it's possible for a set of instructions to put the Turing machine into an infinite loop. This is actually an incredibly important study. Infinite loops are way more important than we've ever taught them to be. We'll come back to that as just a spooky, eerie, infinite loops. How do we use a Turing machine as a language acceptor as we have before? So in the study of compilers, we care about recognizing languages. We just care about recognizing programming languages. So it would be useful to derive a program and show what theoretically a compiler looks like. So we want the Turing machine to accept a language. Let's start with just the study of basic languages to see how that would happen. And then you could start to think about how could I bridge what I know about the programming languages that I write in and the theory of a Turing machine to construct a programming language acceptor. So the string W is going to be written on the tape. Blanks are every space not used by the string. We are going to assume that the machine starts in its initial state, probably something called Q0. The read head is going to be the read write head positioned at the first character of that string that's written on the tape. We will accept the string if and only if the Turing machine is in a final state and the Turing machine has halted. We do not allow blanks on any portion of the string itself. So if you need some kind of separator character that says, here's part 1 of the input, here's part 2 of the input, here's part 3 of the input, do not use a blank. Use anything else. If we allowed them, you can think of the issue that we would run into. We don't know when we see a blank if there's more input on the other side of the blank. So we'd have to go check. We see another blank. Is that intended or not? We have to go check. We would never halt. We'd create our own infinite loop just in trying to read input. So if W is not in the query language, we'll have 2 possible ways to indicate failure: halt in a non-final state and enter an infinite loop and never halt. If we could identify that we were in an infinite loop, then we would know to reject. We'll come back to that idea of identifying that we are an infinite loop, trying to figure out the complexities of that problem momentarily, because that turns out to be a really important study in computer science. Can we identify that we are in an infinite loop? Put that question on the back burner and think of, could you write a program to identify, I'm going to give you as input to that program another program. Your task will be to simulate the execution of this program and return, yes, this program enters into an infinite loop, or no, this program does not enter into an infinite loop. Just pose that out there, and we'll come back to it in a while. All right, let's now move into writing a Turing machine program. We'll make a very simple language here, 0, 0 star. So now, of course, the language is just zeros, or the alphabet for this language is just zeros. Maybe it's zeros and ones. So this accepts any string with 0 or more zeros and nothing of any other character. So first of all, how many internal states are we going to need for this? Just 2. 2 is correct. We're going to have 1 state searching and 1 state denoting we are done. Now the harder part, what are the transitions? So go ahead and spend a little bit of time trying to create the transitions in your mind between these 2 states. Assuming we start in a state that says we are searching, what are the transition rules that we would need to write to be able to accept this language?
Are we given the alphabet as 0?
Let's assume that it's 0 and 1. And in fact, it actually does not matter for this what the alphabet is. That's kind of it. We don't have to write a transition for any other character because no other character could lead us to acceptance. So if we don't define what happens on a 1, we automatically reject if we see 1.
I was thinking if we do the so serious, we can do an early acceptance after the first one.
Right. That would be true. Let's assume that there is some other character that we might see. But when we reach a blank, we know that the string has ended. So we know we need to read that very first 0. So it only makes sense to write that as the first transition. What happens when we're in state Q0 and read a 0? That is the input tuple that we need to define that transition. What is the output triple?
It'd be Q0, 0, R.
Yes. So that is the first transition here. When we're in state Q0 and we read a 0, we want to remain in state Q0, write a 0, which does not change what's on the input. We're reading a 0 and writing a 0, which is the equivalent of a no-op. And we're going to move to the next character in the input. What else do we need to be able to read in order to do this?
Blanks.
Yes, we need to know what to do on a blank. What should we do on a blank?
Parentheses to Q1.
Yeah. What do we write?
A blank.
Yep, you write a blank. Do we move left or right?
Left.
It actually does not matter. But yeah, left would get you back toward the string. So this last character can either be left or right. That doesn't matter. So this is about as simple a Turing machine as I could come up with. 2 transitions. How do we feel about the transitions and about this reading this language? Question?
Couldn't that accept the empty string? Just start at Q0 and then just read the blank.
We could. You're absolutely right.
Just add an intermediate state after you write the first 0.
Yep. So we might need 3 states here. How about a Turing machine for a to the n, b to the n? Such that n is greater than or equal to 1. To start this process, here is my hint. Before you start writing transitions, think about it in English, think about it in terms of logic, because this is a little bit more involved. If you have a Turing machine and you were, I guess, puppeteering that, what positions would you be doing? What would you need to be storing in your mind as you do this? What do we know about the first character?
It must be an A.
It must be an A. What do we want to do with that A? We want to pair it with some kind of B. We want to know that there is a B that comes after a bunch of A's that it is paired with. So you can imagine now, you would need a state that says, I'm looking for an A. You would need another one that says, I found an A, and I am now searching for the associated B. Then you would need another state that says, I found the B, I'm now back to searching for another A. So this is going to end up being more complicated than you probably think it starting out would be.
Idea for how it would work.
Talk to me.
So you start reading A's, turn them all into B's, and then once you reach the end, you find your B's, and then at that point you reach a blank, and then you start going left. And then once you have that, you just keep searching, and once you find a blank going to the left, then you would accept at that point.
How do you know there were an equal number of A's and B's? Because if you're turning the A's into B's,
B double.
yeah, you have no way of knowing what was originally a B and what was originally an A.
That's
to
some
be able
sort of
to-
marker at the end of the A.
That's a good idea.
About that.
Yeah, we need some way to know that we're in between A's and B's, and we need some way of knowing how many either A's that have been seen and A's that haven't been seen, B's that have been seen and B's that haven't been seen.
Take a while to write all the transitions for this, but with the idea of starting at an A, skipping until we see a B, then from there going left and right repeatedly, finding a B and then finding the A every time, removing a character.
You
Making
could
sure every
you
time
could
we
remove them,
bounce,
sure.
Just to make sure we're
Yeah. You could start, look for the leftmost A. As you find that, turn it into a blank, move all the way to the end, see if that's a B.
I was thinking of doing it from the inside out, but that would also.
Yeah, you could also do it from the inside out. That becomes a little bit harder because you see your first B, you turn it into a blank, you read an A, you come back and you see a blank. Are there more B's on the other side of that blank?
Oh, that's great.
Then we end up back in that infinite loop. If you're using blanks as a possible writing symbol for that, then you create that level of ambiguity. So if you do it outside in, that's a little bit safer. There is a way to do it inside out, which would minimize the time. You're not going over twice as many characters as you need to. It's inefficient to do that rightmost B when you could look at that first B. How could we do that? There is a way to move left to right on both A's and B's. What does that require? We can even use what's directly on the tape. We just need more characters than A's and B's. This is why we distinguish between the input alphabet and the tape alphabet. We can use additional characters here. So we're going to define X and Y. X represents an A that we have seen, and Y represents a B that we have seen. And now an A represents an A we have not seen, and B represents a B we have not seen. So we can move the read-write head left, should say right, until we see the first B. So is the first character an A? If so, replace it with an X, saying we've seen it. Now we're going to move right, searching until we see our first B. When we see that B, we are going to replace it with a Y. Then we're going to move back left until we see an X. When we do that, we're going to move right and look for an A. If that's an A, we replace it with an X. Move all the way to the right until we see our first B. Once we see a B, then we're going to replace it with a Y. Move back left until we see an X. Move right. Is it an A? Continue that process of replacing A's with X's and B's with Y's until when we're moving back looking for an A and we see a blank. That means we have read all of the A's. Or if we're moving right, waiting for a B and we see a blank, that means we've fallen off the end. But the only reason that we are moving right and searching is if the A's have been exhausted. Sorry, if we found an A and we're looking for an associated B. If we're in that case and we fall off the end, we should reject because there were more A's than B's. So the string can't be A to the N, B to the N. The last thing to do is we go back and we see that there are no more A's. We actually need to go back right one last time and ensure there aren't any more B's on the right-hand side. Because otherwise we'd accept A to the N, B to the N plus some number of B's, and we don't want that. So here is the basic idea. So those are all of the associated rules. So now that we've gone through all of that logic, we're going to come back tomorrow and try to write that program. There's a lot. There's a lot of transitions associated with that, but I think that that serves as a good exercise. So we'll come back tomorrow and do that. Questions or concerns as we pack up?
I guess like in the class, is there ever gonna be a point where we go over like when it makes sense to use like one top of it over another for efficiency purposes? Because this could definitely be
yes.
represented with something similar.
Yes. So we're going to talk about all of the different language classes. We're going to zoom out and look at all of the different language classes, what they can compute. And in general, you want to use the simplest language class that a language could be represented as. So this is a context-free language. It would make much more sense to represent it with an NPDA than with a Turing machine. That said, if I gave you a language that can only be accepted by a Turing machine,
And you don't have a choice.
you don't have a choice, but the program is so complicated. Or it might be so complicated that it's difficult to use as a good introductory example. So we will come back to it, but I want to start with some of the simpler languages so that we can get some practice building Turing machines. But we will come back to that idea of what are these different classes of languages? But there are some we haven't even talked about yet.
Thank you.
Thank you.